All right, hi y'all. Today we're going to be taking a look at Riemann sums, so ways to estimate a definite integral. So Riemann sums and trapezoidal sums. So here we go. These are the ways that we're going to estimate under the area underneath the curve. A Riemann sum, I always think about that R for Riemann, which is just some guy's name. Riemann stands for rectangle. You're going to be splitting the region into the number n subintervals, the number of rectangles. Okay, so Riemann sums are rectangles. And then if it's a trapezoidal estimate, they'll have to say the word, use a trapezoidal sum. So it's basically telling you that it's trapezoidal. Okay, n is the number of subintervals that you're going to split the region into. Okay, so for all of our examples here, we were looking along this curve and we were going from 0 to 2. So from 0 to 2, and we were splitting it into 4 subintervals. That's why you'll see 4 rectangles for each of these. Right? So for Riemann sums, they're going to have to tell you what type of Riemann sum. Are you doing a left, a right, or a midpoint Riemann sum? Okay. So a right Riemann sum is where we use the output of the right endpoint as the height. So if we're going from 0 to 2 and we split it into 4 rectangles, right? That would mean from 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. If we're doing a right Riemann sum, we're going to get the height at the rightmost point. So we're going to be like, okay, from 0 to 0.5, 0.5 is the rightmost, so we're going to use the height. If I plug in 0.5 into the function, right, here's f of 0.5, right, I'm going to use that at the height, for the height of the rectangle, right, so the base times the height, the base times the height, and if it's a right Riemann sum, I'm going to use the height at the rightmost point, right. If it's a left Riemann sum, we're going to use the height at the leftmost point, so it'll be like, okay, from 0 to 0.5, I'm going to use the height at 0. At 0.5 to 1, I'm going to use the height at 0.5. Okay, but it's constantly just base times height, base times height, base times height. Right, so it'd be like base times height plus base times height plus base times height plus base times height. We're basically going to take those 4 bases and heights and multiply them all and add them up. Right. I don't know if you can see here, because this function was increasing, right, you can see that the right Riemann sum included some area that should not have been included, so that will end up being an overestimate. The left Riemann sum, because it was an increasing, right, all this space in here should have been included and was not, so we'll know that is an underestimate. And then the midpoint Riemann sum. Midpoint Riemann sum is, instead of using the left or the right, they use the midpoint. So in between 0 and 0.5, we take 0.25, whatever the height at 0.25 is, that's going to be the height of that rectangle. Right? In between 0.5 and 1 would be 0.75. We're going to use the height at 0.75. Right? Hopefully you can see the power of the midpoint Riemann sum is that if you use the height at the midpoint, you're going to end up including some that should not be included, but it balances out pretty nicely the stuff that should not be included. So midpoint Riemann sum is a little bit more accurate normally than a left or right Riemann sum. Okay. And I'll show you in the examples how you're going to show all that work out. Yeah? For a trapezoidal sum, so a trapezoidal sum, slightly different picture, but same idea, is that you're splitting the region into trapezoids instead of rectangles. So if you're trying to estimate the area underneath the curve, but it asks you to use trapezoids, you're going to use the trapezoid area formula. So that's the first thing to do, is talk about what the area of a trapezoid is. So the area of a trapezoid, and we should have this conversation, back in geometry when you saw trapezoids, most of your trapezoids were probably sitting like this. This is probably what your brain thinks of when you see a trapezoid, right? Kind of sitting sideways. What we're going to do is take that trapezoid, flip it on its side, and flatten one of the sides. So you can see kind of this is like a typical trapezoid. So if you like come up one side here, connect, come down. Technical definition of trapezoid, right? One set of parallel lines. So in our case, the set of parallel lines are going to be the ones going up and down, vertical. Okay. So we're going to take this on its side and flip it. So, what used to be, like, we used to call this like the height, and this would be like base 1, and this would be like base 2. So back in the day, you may have memorized that the area of a trapezoid is always 1/2 of the height times the sum of the two bases, base 1 plus base 2. Right? But because we're going to orient it sideways, you may want to memorize it slightly differently. So you may want to memorize it as there's just one base, and then you have these 2 different heights. And really all you're doing is averaging those 2 heights to create a rectangle. And so you're going to add h1 plus h2 divided by 2, and then multiply it by the base. Right? So 1/2 of the sum of the heights, h1 plus h2, and then multiply it by the base. So if I just say 1/2 base times h1 plus h2. or the sum of the heights times the base divided by 2. However you want to memorize it, you got to know the trapezoid formula. Okay. And so for trapezoids, hopefully you can see the same idea. We're estimating the area underneath the curve. Sometimes, right, the trapezoids will lie beneath the curve, and so there'll be space that you should have included that you didn't, right? And sometimes your trapezoids will lie above the curve, and you'll include stuff that should not have been included. Maybe take a moment and see if you can figure out what the difference is. We'll cover it in a second. All right, and so here are these official rules, right? What are the rules for knowing if the estimate will be an over or an under estimate? Right? So for Riemann sums, so for rectangles, what matters is if the function was increasing or decreasing, right? If for trapezoidal sums, it'll matter if the curve was concave up or concave down. So why don't I just cheat and put up the answer key here. So this is what the rules will be for knowing if our estimate is an over or an underestimate, right? Again, like we mentioned here, if the function was increasing, then a left Riemann sum would underestimate it, but a right Riemann sum for an increasing would overestimate, right? All these values here would be over the actual area. Versus if the function's strictly decreasing, right? Let me move this over so you can see a little bit more. Then the left-hand Riemann sum would be an overestimate, and the right would be an under. So vice versa of the right one, right? And the trapezoidal sums, the estimate will have to do with the concavity. So if f of x is concave up, right? Here's that scenario. Here's a concave up curve, right? Trapezoids will always overestimate this because I would include all of this area in there that really shouldn't be included. So that'd be an overestimate. And if it's concave down, then the trapezoids will be an underestimate. Okay, and traditionally this is one of the students' favorite sections because it's pretty doable, right? You guys just scan and find the words. It's always when a table is given. So when a table is given in a free response problem or in a multiple choice problem, right? And they ask you to estimate a definite integral, and they'll say either using, you know, a left or right, a midpoint Riemann sum or a trapezoidal sum. So scan for that. And then you're going to, you know, to kind of explain what was happening based on the scenario. Okay? So typical rocket launch problem. So we have rocket A, maybe pause and read it on your own. But let's talk about a rocket that has a positive velocity after being launched upward. It's giving you some initial height of 0 feet at time equals 0 seconds. The velocity of the rocket is recorded for selected values from 0 to 80 seconds. Okay. So we want to estimate the integral from 0 to 80 along v of t dt with 4 subintervals, right? So this is telling you n equals 4. That's telling you how many rectangles you're going to have. And it says by using a midpoint Riemann sum. So a midpoint Riemann sum, right? Using correct units to explain the meaning of the integral from 0 to 80. All right, so first off, let's think about, you know, we're going from 0 to 80, and they're giving us data every 10 seconds. Right? So just for like a rough sketch, this does not need to be a perfect, but if you can imagine going from 0 to 80, right? And they've asked us to split it into 4 subintervals, right? So 4 subintervals. If we want to know the width of our rectangles, so the width of the rectangles, there's a little formula, and we will be using this formula throughout the next few sections. So if you're taking an integral and you're going from A to B along some function, f of x dx, right? Then the width will always be the big value minus the small value, so b minus a, all divided by n, the number of subintervals that you're working with, right? On this problem, our b value is 80, so we have 80 minus our beginning value is 0, and we're dividing it by 4 subintervals. So 80 divided by 4, hopefully we're comfortable that our width should be 20 for this problem. So the width of all of our rectangles would be 20. So we're gonna go from 0 to 20, right? 20 to 40, 40 to 60, and then 60 to 80. Right, let's label that there. So we know our widths would be 20. It would not matter if this was a midpoint, a left, or a right Riemann sum. If they gave us this data, then, and the width of each rectangle had to be consistent, then it would be 20. All right, now because it's the midpoint Riemann sum, we're gonna think about what the midpoint is. So from 0 to 20, we're not picking either of those. We're gonna pick the height at 10, right? So we wanna know how tall is this at 10? That's what we're gonna use the height for the first rectangle, right? The second rectangle, we're going to use the height at 30. Whatever the height is at 30, we'll use that, right? The height at 50, we'll use that height, and the height at 70. right? So the height at 70, the height at 50, the height at 30, and the height at 10 is what we care about for this problem. So what you have to show for your work for these problems is the setup. So I'm going to squeeze it in right here. I'd be like the integral from 0 to 80 along v of t dt is approximately equal to, and because it's 4 subintervals, basically I need to see base times height, 4 base times heights. So base times height plus base times height plus base times height plus base times height. That's what you need to write out every time, right? We already saw that our bases every time we're going to be 20, right? So 20, so I'm just going to fill in each base being 20. And then again, the height, because it was a midpoint Riemann sum, I'm going to use the height at 10. So the height at 10, which was 14. And then the height at 30, which was 29. The height at 50, which was 40. And the height at 70, which was 47. Now remember in this class, that setup is perfectly fine for your final answer. You don't have to calculate and get like the actual numbers. Let me look at the answer key and find out what the actual numbers were. So let's see, if you actually did all the math on this, this was approximately equal to, or actually equal to 2,600. So 2,600. We'll talk about units, right? When we are taking a definite integral, we are multiplying, which we'll look at our definition more a little bit tomorrow, but that's what this is saying. F of x, this is saying like what the height was at any given moment, and the dx is the width. We're truly multiplying the height times the width, and we're adding all of those up from A to B. Okay, so if we were going to multiply these units, this is feet per second times more seconds, right? So this is feet per second, and we're multiplying by more seconds. Hopefully you can see the seconds would cancel, and you're literally just left with feet. Okay, so this would represent 2,600 feet, and I'll show you my final answer in a moment, but that would represent that the rocket traveled that many feet during those 80 seconds. So let me erase and put that answer up real quick. So, you know, in terms of like the work you would need to show for a problem like that, you'd have to show your setup. So notice I have the base times the height, the base times the height, base times the height, base times the height. And my explanation, because it asked, you know, what does this mean? I said the rocket traveled that many feet during the time interval from 0 to 80 seconds. So you'll have to have both the units of the object, so the feet in this case, and then the time units. They were seconds. Remember, again, you don't have to find the 2,600. So that's why I was modeling, like you could literally say that the rocket traveled this many feet. You don't have to like repeat it or rewrite it out. Okay. I don't know if that makes sense, y'all. Feel free to try the next one on your own if you're feeling ready. Example number 2 is about a spherical balloon, hot air balloon, expanding, and the radius of the balloon is modeled by this twice differentiable function. So maybe something new and different on this problem is that it's t versus r prime of t. So this is already a rate, right? This is in feet per minute. That was also already a rate. It just didn't have a prime on the notation. Right? This one's asking for a left Riemann sum. So a left Riemann sum. Again here, 5 subintervals. So 5 subintervals. And the data in the table going from 0 to 12. Right? Now realize here, if I try to use this formula like I did on the last one, the width being b minus a over n, I could try this. I'd be like 12 minus 0 over n, which was 5. That would be 12/5. Right? I don't have every 12/5 data on this problem, right? I have random data. I have from 0 to 2, and then I have 3 seconds later at 5, and then 2 seconds later at 7, 4 seconds later at 11, and then 1 second later at 12. So this table is dictating the 5 sections. I have 6 data points. Those are my 5 sections, right? If you ever get stuck, feel free to like draw yourself out of a picture. But if you can imagine, if you're here at 0, and then again here at 2, and then again here at 5, and then again here at 7, and then again here at 11, and again here at 12. You can imagine chunking those up as rectangles, right? The first base is here, that has a base of 2, right? And then this has a base of 3, so you're going from here to here would be 3, right? From here to here would be 2, from here to here would be 4, and from here to here would be 1. You can see those differences in the table. So it's often how I'll show my work, is showing kind of that the change in here from 0 to 2 was 2, was 3, was 2, was 4, and was 1. So I know those are my bases. And then this said we wanted a left Riemann sum. So on this one, I'm going to use the height at 0. I'm going to use the height at 2. I'll use the height at 5. I'll use the height at 7. I'll use the height at 11. I'm not going to end up using the height at 12. So keep that in mind that you should not see 0.5 being used as a height. So if I was going to show my work on this, I might say that the integral going from 0 to 12 along r prime of t, dt, right, is approximately equal to, so base times height plus base times height, I'm going to have 5 of them this time. Base times height, base times height, base times height. And now this time I know my bases will be the difference of my x values. So 0 to 2 will be 2, 2 to 5 would be 3, 5 to 7 would be 2, 7 to 11 would be 4, and 11 to 12 would be 1. And then again, this is a left Riemann sum, so I have to use the height at the leftmost point. So the height from 0 to 2 is 5.7. Right. From 2 to 5, I'm going to use the 4.0, the 2.0, the 1.2, and then the 0.6. Okay, because it was a left Riemann sum, notice you did not use that rightmost data point. If we look at the answer key on this, it looks like it ends up being 32.8, and therefore what the answer was meaning, right, that the radius of the balloon expands 32.8 feet over those 12 minutes. All right, y'all, hope that's making sense. That was a left Riemann sum. Guess what's next? All right, maybe if you want to try this one out. This is a right Riemann sum. So maybe why don't you go ahead and try. And I'll just put the answer up for this one. So this one's a little boring. There were no units. So not the most exciting, but let's see how we did on this. The integral from 0 to 10 along h of t, right? Here, let me show you how you use the table to kind of find the widths, right? So going from 0 to 2, you had a difference of 2. 2 to 5, difference of 3. 5 to 7, difference of 2. 7 to 10, difference of 3. So notice that those show up in my bases. So there's the 2, the 3, the 2, and the 3. And then because this is a right Riemann sum, I knew I wasn't using the leftmost data point. So I used the 10, the 15.5, the 18.5, and the 20. Okay, so there's the 10, 15.5, 18.5, and the 20. If you actually multiplied and added those up, it looks like it was 163.5. Right? And the units on this, oh, there were units, but it's just weird, right? Units not asked for because inches times minutes means nothing, I said. Right. Then the second question though said, is this approximation greater than or less than the actual integral from 0 to 10 along h of t dt, right? Give a reason for your answer. So they had told you that h was an increasing function, right? So here's my visual. If you have an increasing function and you're using a right Riemann sum, see how all this space up here actually should not be included, but it is being included, so that would be an overestimate, right? So I said because h of t is increasing, and we used a right Riemann sum, we know the estimate would be an overestimate of h of t. All right, and then example number 4, last but not least, guess what we have, right? A trapezoidal sum. So this is about a customer at a gas station, right, has pumping gas into the tank, right? This is the rate of flow of gasoline is modeled by this differentiable function, right, and given in the table. So using correct units, interpret the meaning of the integral going from, ooh, and careful on this one, it didn't start all the way at 0, right? Going from 60 to 135. So from 60 to 135, right? It's asking for the for an estimate of that, and then find the interpretation, the meaning of it, right? So the integral from 0 to 135. So we're looking at these, and I don't know if it told you, it did tell you 3 subintervals, right? So going from 60 to 90, 90 to 120, and 120 to 135. So widths are going to be 30, 30, and 15, right? And then because it's a trapezoid, you have to use the trapezoidal sum instead of base times height, base times height, base times height. Okay. So on this one, just going to look slightly different, but it's the same idea. But you can see that the formula for the area is a little bit more complicated, right? So instead of writing just base times height every time, if you can kind of imagine my skeleton, it's kind of like, okay, 1/2 of the base, and then times the sum of the two heights, plus 1/2 of the base times the sum of the two heights, right? Plus 1/2 of the base times the sum of the two heights. It's kind of what I start off with every time when I do a trapezoid. Biggest mistake, students want to minus. Remember, it's the average. You're averaging like the two heights and then multiplying. So again, the widths were the difference of the table values, the x values. So 90 minus 60 was 30, 120 minus 90 was 30, 135 minus 120 was 15. And then you're adding up those values. When you actually add those up, if you choose to, right, it looks like it was 8.625 gallons. And therefore, that was the number, total number of gallons that go into the gas tank from from 60 seconds to 135 seconds. All right, y'all, just finding areas underneath the curve. Hope that made sense. Bye.